Good afternoon. Today we're going to discuss Chapter 5, which is about work and energy. Observe the man in the picture. What he's doing. He is pushing the boulders up the slope. Of course, he is applying a force. If the applied force is large enough to counter the weight of the block or the boulders, he can move these boulders to a certain distance. The distance, of course, will be parallel to the direction of the force. So force times distance is equal to work. And energy, as defined from our physics, is the capacity to do work. So let's now go to the application of work-energy equation for rectilinear translation. From Newton's second law of motion, so we know that the net force acting on a body is equal to the product of the mass and acceleration. We can express mass in terms of the weight and acceleration due to gravity. And also, from differential calculus, we know that A ds is equals to V dv. A being acceleration, V is velocity, ds is differential distance, and dv is differential velocity. From the first equation, it equates the resultant force acting at any instant to the corresponding acceleration. And the second equation expresses the instantaneous value of the acceleration in terms of the instantaneous velocity. Now, eliminating A in the two equations, so you can solve from the second equation the value of A. So V dB over ds. And substituting to equation 1, so we will have this equation 3, summation of forces along x times ds is equals to W over G times B dB. This is now the differential form of the work-energy relationship. Integrating equation 3 and assuming that the initial velocity is v sub o at zero displacement and that final velocity is v at a final displacement s. So integrating the left side of the equation, the limit would be 0 to s, and integrating the right side of the equation, W over G is constant, the limit would be v sub o up to v. So this will give us equation that is the net force acting on the body times the distance is equal to 1/2 Wg v squared minus 1/2 W over G v sub o squared. We can factor out W over 2G. So the inside the parenthesis would be b squared minus b sub o squared. This is now the change in energy. And on the right side is the work. So work is equal to the net work acting on a body is equal to the change in energy. So the left side of the equation is the resultant work and the right side is the kinetic energy or change in kinetic energy. This is square of final velocity minus the square of the initial velocity times W over 2G, that is now energy. So if the force acting on a body is constant, so we can write the equation to be the net force times distance is equal to the change in kinetic energy. So we have here equation 5.2. So what is the unit of work? So that is force times distance, so that would be Newton meter. And Newton meter is equivalent to joules or joule. Another unit for work is foot pounds, pounds inches, dyne centimeter or tan feet. But it is convenient to use Newton meter or foot pounds. Okay, what do you mean by work? So let's consider this block resting on an inclined surface. So of course, there's the weight of the block. Since the surface is inclined at an angle theta, the weight is directed downward. It will have a component normal and tangent to the inclined surface. Suppose there is applied horizontal force P applied to the block. So the angle of inclination with respect to the inclined surface is also theta. And the reacting forces at the bottom of the block would be the normal force, which is equal to the normal component of the weight, and the force of friction, which is coefficient of kinetic friction times the normal reaction. We can determine the work in two ways. That is, using the component of the force parallel to the inclined surface, and then multiplied by the distance along the inclined surface. So work is P cosine theta times S. If we use the horizontal force P, so we need the horizontal distance. So that is S P times the distance S cosine theta. But we have this vertical distance. There is a force that is against the work. That is the weight of the body times this distance. That's negative work. And the positive work is produced by force P. So this would be the equation for work energy equation being done on the block. The net force is equal to P cosine theta minus W sine theta times minus the force of friction. That is the net force acting. So P cosine theta is positive force. It will push the block up the incline. The horizontal component or tangential component of the weight is a negative force because it is preventing the motion up the incline, and the friction is always negative. We multiply that by distance, so that is work. Equals to the change in work. P cosine theta times S minus the tangential component of the weight times distance minus the force of friction times distance. So these two are producing negative energy. This is positive energy. Okay, so let's go to the application of work energy method with constant forces. Okay, suppose there is a cart that moving along the inclined surface, the distance is S sub 1, and then it will move along horizontal surface, the distance is S sub 2. Considering this portion, the inclined portion of distance, so initial velocity is b sub o, and at this point is b sub 1. Moving along the horizontal surface, the initial velocity is b sub 1, and the final velocity is b sub 2. So what would be the equation? So we can write the work energy equation for S sub 1, and then another work energy equation for S sub 2. Then adding the two equations, so that is the work energy equation for the whole system. We have to write the work energy equation to the whole system, not only for the portion. You can write equation on every portion, on every segment, then you have to combine. Then that is the total work energy equation for the system. So the procedure on how to apply work energy method for constant forces. First, determine the direction of motion. Confirmation is obtained by noting that the resultant work must be positive to speed up the system, and vice versa, meaning all forces opposing the motion is negative. Determine the kinematic relation between the bodies composing the system. and then apply the work energy equation to the entire system. If the internal force in a connecting member is desired, so apply the work energy equation to a free body diagram of that part of the system on which this force then acts as an external force. If the internal force is not constant, however, this step will determine only its average value. The instantaneous value of a variable force must be found by the force inertia method. Let's have here sample problem 1. What force P will give the system of bodies shown in the figure a velocity of 30 feet per second after moving 20 feet from rest? So this is the diagram. So we have here a 100-pound block. Then a cord is attached to it, passing through a frictionless pulley. Then at this point there is 200 pounds. And then another cord passing through a frictionless pulley attached to a block 50 pounds weight. And then this is the applied force P. So in this case, we need the internal forces acting on the body. So we have to draw the free body diagram of each block. For 100 pounds, so the motion is definitely along the horizontal and directed to the left. So let's say the tension is T sub 1. And there is friction on the surface. So force of friction is in the opposite direction. For the inclined surface, the block on the inclined surface. So let's say this would be T sub 1. This another cable here, T sub 2. And then the weight, it will have its component normal and tangent to the surface. And then there is F sub 2. Transferring to 50-pound block. Okay, this tension should be T sub 2. And this is F sub 3. And then there is force P here. So if after constructing the free body diagram, so it would be easy to solve the problem. We have to apply work energy equation for each block, separate from each other. So this is the general work energy equation. Considering the first block, so T sub 1 minus force of friction. What is force of friction? Coefficient of kinetic friction times the normal reaction. The normal reaction is equal to the weight of the block. Okay, that is the net force times distance 20 is equal to W over 2G times quantity, the square of the final velocity minus, it starts from rest, so initial velocity is 0. So in here we can solve for T sub 1. Considering this block on the inclined surface, so the motion is up the incline, so T sub 2 will be positive. T sub 1 negative, F sub 2 is negative, and the normal component of the weight is also negative. So that is the work energy equation is T sub 2 minus T sub 1 minus force of friction, 0.2 times normal reaction, that is equal to 200 cosine 45, equal to the normal component of the weight, minus 200 sine 45, that is the tangential component of the weight. Okay, times 20 is equal to the work. So the weight is 200 over 2G times 30 square minus initial velocity is 0. So you can solve for T sub 2. And for the last block, 50-pound block, so this will produce, P will produce positive work, T sub 2 and F sub 3 will produce negative work. So P minus T sub 2 minus force of friction, that is 0.2 times 50 times the distance is equal to the change in kinetic energy. So from that we can solve for P, which is 444.27 pounds. So that's easy. Draw first you have a system of block. So you need the internal force. So you have to draw the free body diagram of each block and then apply work energy equation. So let's solve another example. Find the velocity of body A in the figure after it has moved 10 feet from rest. Assume the pulleys to be weightless and frictionless. So this is the the pulley. We have solved this already in chapter 2. Okay? But this time, we will apply work energy equation. So what should be the movement of the block? So you can make assumption. And if the result is negative, so that means in the opposite direction. Assuming block B will go down, so the block A will move up. Okay, so the free body diagram of block A, so you have tension at A, then the weight. Then for the pulley, so this would be tension at A, and then 2 tension at B. If this is frictionless, there's only one tension in the cord. And this would be free body diagram of block B. So applying work energy equation, so you can see from this diagram that T sub A is equals to 2T sub B. So that is equilibrium equation. In that case, since the tension at A is twice the tension at B, the distance covered by the block A is only 1/2 of the distance traveled by B. So as with the velocity. Velocity of A is 1/2 velocity of B. Okay. If there are 3 tension here, T sub B, so T sub A is 3 times T sub B. And S sub A is 1/3 of S sub B. B sub A is 1/3 of B sub B. So remember that. Now we have here the work energy equation. So let's apply this to each of the block. First, block A. So T sub A minus the weight. The weight is against the motion. The motion is upward. T sub A minus 300 times 10. That is the distance traveled by block A. Is equal to 300 over 2G times B sub A squared minus 0. Simplifying, we have equation 1. Then apply work energy equation to block B. That is, the motion is downward, so the weight would produce positive work, and the tension would produce negative work. 200 minus T sub B times 20. The distance traveled by B is twice the distance of A. Okay, so it would be 20. Equals to the weight over 2G times B sub B squared minus 0. What is B sub B? That is twice the velocity of A. So substitute the equivalent of T sub B, that is 1/2 of T sub A. The equivalent of B sub A, 1/2 of B sub B, or B sub B is twice B sub A. Then we have equation 2. So we have 2 equations to know, so just press your calculator, mode 5, equation 1, and it will give you the answer B sub A equals to 7.65 feet per second. You can also solve for T sub A, but what is required here is only the velocity of body A. Now, for the resultant work, if the force applied is variable. So you can draw the force displacement diagram, or we call it the motion diagram. So the general form of the work energy equation is equal to equation 5.1. We need the resultant work, and that is equal to the change in kinetic energy. So let's have this spring. So when you apply axial force to the spring, definitely it will elongate depending on the value of the spring modulus. And you can draw the motion diagram. So from that motion diagram, we can write the equation from Hooke's law. You are familiar with this in strength of materials. P equals to Ks. P is the applied load, K is the spring modulus, and S is deformation of the spring. So from the figure, the net force applying energy equation. So the net force is equal to 1/2 Ks times S. Ks, how we do this? By integration. Okay? So the equation for the spring, the energy in the spring is 1/2 Ks squared. You integrate the energy equation. Okay. So from the force displacement diagram, the resultant work is the area of CDF. CDEF. So what's the area? So the resultant work is Ks1 over Ks2. Ks1, Ks2, Ks1 divided by 2. So you are solving for the average. Times the difference in distance, S sub 2 minus S sub 1. Where K is the spring modulus. So let's have a sample problem. A block weighing 96.6 pounds is dropped from a height 4 feet upon a spring, whose modulus is 100 pounds per inch. What velocity will the block have at the instant the spring is deformed 4 inches? So this would be the diagram. So you see the spring, then the block is 4 feet above the spring. If you drop, meaning the initial velocity is 0 to the spring, once it reaches the spring, definitely the string will deform. And the deformation is 4 inches. So what is the total distance traveled by the block? So that is 4 feet h plus the deformation of the spring 4 inches. Minus the resistance of the spring, 1/2 Ks squared, is equal to the change in kinetic energy. So the weight is 96.6 multiplied by 4 feet plus 4 inches. So divided by 12 to convert to feet. Minus 1/2 times K, 1,200. Why is it 1,200? It's 100. Convert this to feet. Pounds per feet, you have to multiply it by 12. So it's 1,200 pounds per foot. Multiplied by the distance is 4 over 12 in feet square. Equals to W over 2G. Drop from the height, so initial velocity is 0. So times V squared. So from that, you can solve for the velocity of the block at this point when the spring is deformed 4 inches. So that's the. So another sample problem. The rigid horizontal bar shown in the figure is supported by 2 springs. A 300-pound weight is then placed upon the bar B. The bar at B. A sudden blow projects the weight towards A with an initial velocity of 6 feet per second. What is its velocity when it reaches A? Neglect friction and the weight of the bar. So this is the diagram. Okay. Spring modulus for B is 50 pounds per inch. Spring modulus is for A is 100 pounds per inch. The distance between the two springs is 10 feet. Okay, so let's write the work energy equation. Okay, so what are the forces acting on the spring? So that is simply the weight. And then we consider the resistance of the spring. It is a rigid horizontal bar. So, meaning, and the applied force is sudden. So, when the block is at point A, so the forces are 300 plus this K, 100 times 12, so that is pounds per foot, times the distance S, the compression of the spring. That is the total force acting at A. Is equal to the force here when the block is here. 50 times 12. So to convert this to pounds per foot times the deformation of the spring. Equating the two is equal to negative, deformation of spring is 0.5 feet. It's negative, definitely, because it will be compressed. When the block is at A, this is rigid bar, so it will remain horizontal. That's why the force here is equal to the force here. Okay, and then applying work energy equation. So this W over 2G times B squared minus 6 square, initial velocity, plus 1 half Ks squared. 100 times 12 times S is negative 0.5 is equal to the work here. The final work is equal to the initial work. So 1 half 50 times 12 times the deformation 0.5 feet. So from that, we can determine the final velocity, 4.46 feet per second. Okay. So let's go to the next, that is power and efficiency. Those who have hydraulics, you know this, or if you remember your physics, you know what is power and what is efficiency. Power is the time rate at which work is done. So that is work divided by time. An example is, if a train is being pulled by a locomotive, the work done on the train may be measured by the work done by the drawbar pull. So power is work over time. So that's average power. For variable forces, the work during any instant is the net force acting on the body times the differential distance. Or simply that is equal to F times differential distance, where F is the net force doing the work. The power exerted at any instant is work over time. So substituting, that would be F ds over dt. Or simply that is equal to force times velocity, because ds over dt is velocity. So you have equation 5.3. So for power, we have also this what we call efficiency. The ratio of power output to power input. So you multiply this by 100, so that efficiency would be in percent. The unit for power is watt. 1 watt is equals to 1 Newton meter per second, or 1 joules per second. 1 horsepower equals to 746 watts, or 746 Newton meter per second. In English unit, 1 horsepower is 550 foot-pound per second. Multiplying that with 60, so 1 horsepower is 33,000 foot-pounds per minute. Let's have here a sample problem. A train weighing 100 tons is being pulled up a 2% grade. When you say 2%, though, so that is, let's say the distance is in meter. So 2 meters for vertical distance for every 100 meter distance. The train resistance is 10 pounds per ton. The speed of the train is increased from 20 feet per second to 40 feet per second in a distance of 1,000 feet. Find the maximum horsepower developed by the locomotive. So, applying work energy equation. Let F be the force exerted by the locomotive minus the resistance. 100 pounds per ton times the weight of the, or 10 pounds per ton times the weight of the train, 100 pounds. Minus 100, that is tons, we convert to pounds, so multiplied by 2,000, times the 2 over 100, the slope. So we are solving for the component of the weight tangent to the surface. That is against the motion. Times 1,000 feet, the distance, is equal to the kinetic energy. 100 tons times 2,000 pounds per tons over 2g. Final velocity, then this is the square of the initial velocity. Solving for that equation, you can solve for the force exerted by the locomotive. Solving for power, power is force times velocity. Of course, we have to use the final velocity. So the power exerted by the locomotive is 349,068.323 foot-pounds per second. So the required is horsepower. So we divide this by 550 foot-pounds per second. So the power exerted by the locomotive is 634.67 horsepower, or approximately 635. So another sample problem. Water flows through a nozzle 1 inch in diameter under the head of 400 feet to drive a turbine. So the turbine is 90% efficient and is connected to a generator which is 94% efficient. What is the power output in kilowatts? So those who have hydraulics, so you are familiar with nozzle and turbine. So the equation for power from hydraulics, or maybe you have discussed this in your physics, that is Q gamma H. Q is the discharge, gamma is the unit weight of water, H is the head. What is this head? An example of this is, suppose you have a water tank elevated at a certain height, connected to the faucet in your sink. Once you open the faucet, so water will flow. And when the water tank is full of water, so the velocity is, what do you call this? Very fast. You can fill a glass in a minute, or shall we say a few seconds. But when the water tank is at the same elevation or lower elevation than the faucet, so when you open the faucet, so water cannot enter in that, will not flow, because the source is lower than the elevation of the faucet. If the source is higher, then that is what we call the elevation head. So equating Q gamma H with force times velocity, so you can cancel velocity. And from that, you know the area, you know, given diameter of the nozzle. So you can determine the force on the turbine. Force is gamma AH. The head is 400 feet. So substituting to the given value to the equation, you can determine the force, 136.14 pounds. And also from hydraulics, and even from differential equation, you know that velocity is the square root of 2gh. Substituting the given value, we can determine the velocity, 160.5 feet per second. So what is now the power input? the input of the nozzle to the turbine. So from the equation, that is power is force times velocity. Converting this to horsepower, so we divide by 550 foot-pounds per second. So the power input by the water jet to the turbine is 39.73 horsepower. Using the equation for efficiency, we can determine the power output of the turbine, 35.75 horsepower. This power output of the turbine will be transferred to the generator. So using that would be the input to the generator. So using efficiency equation, we can determine the power output of the generator. That is 94% efficient. Substituting the given to the equation, the power output of the generator is 33.61 horsepower. The required in the problem is kilowatts, so you can divide this by 746 or watts in 1 horsepower. And then divide by 1000 so that it would be in kilowatts. So the power output of the generator is 25.07 kilowatts. Next, a 100-pound weight is swung in a vertical circle at the end of a 4-feet cord. The topmost velocity of the weight is 12 feet per second. Find the tension in the cord at 120 degrees past top position. And what minimum velocity at the location will keep the weight in the circular path at the top. So this would be the diagram. Starting at point A with an initial velocity of 12 feet per second, rotating in counterclockwise direction. Then it reached point B, 120 degrees from the initial location. So the forces acting on the weight, so that's the weight, 100 pounds. Tangent to this is the mass times the tangential acceleration. And normal to this is the centripetal force. So WV sub B squared over GR. And this would be the tension in the cord. The tension in the cord is always acting normal to the weight. Applying work energy equation at B, so work times distance, so we have to consider vertical distance, is equal to the change in kinetic energy. So what is the work? Weight, 100 pounds, times the vertical distance. So what is the vertical component of this radius? 4 sine 30 degrees. So you can use this one angle, or you can use cosine 60 degrees. 4 sine 30 degrees, so that's the vertical component of distance, plus the radius 4 feet, is equal to the change in kinetic energy. So from that, you can solve for B sub B square. Summation of forces normal to the weight is equal to 0. So the tension is equal to the centripetal force plus the normal component of this weight, normal to the weight. So that is 100. This would be 60 degrees, cosine 60 degrees. This is the centripetal force. So at that position B, the tension in the cord is 461.8 pounds. To find the minimum velocity at the bottom C, to just keep the weight in the circular path at the top A, we note that the tension in the cord will be 0 at A, the highest position. The centripetal force WB squared over GR will just balance the weight. So centripetal force is equal to the weight. So you can cancel the weight. So what will remain is b squared over gr equals to 0 or equals to 1. So therefore b squared equals to gr. Applying the concept of the motion being equivalent to free fall. So that is, this is the from A to C, the total vertical distance is equals to twice the radius. So b sub c squared equals to b sub a squared plus 2gh. This is the equation for freely falling bodies. So what is b sub a squared? That is gr plus 2gh. H is twice the radius. So simplifying, b sub c squared is 5gr. Substituting the given value, so b sub c is 25.38 feet per second. If that is the velocity at point C. So okay. So it will, when it is rotated, so it will reach point A again. Starting from point A to point C, velocity at C is 25.38, then it will rotate again, reaching point A. Okay, now let's apply work energy equation for rotation. So from Newton's second law of motion, that is the total moment or the net moment acting on a body is equals to I alpha. I being the mass moment of inertia and alpha is the angular acceleration. And alpha times d theta is the angular displacement, is equals to W, or that is omega, which is angular velocity times differential angular velocity. So that is similar equation. There is similarity with the equation, work energy equation for rectilinear translation. Only that the linear velocity, linear acceleration will be replaced with angular acceleration, angular velocity, and angular displacement. But the procedure would be the same. But since it's rotation, we have to consider not the linear force, but the moment. Summation of moment times d theta is equals to I times omega times d omega, differential omega. So in here, we eliminate alpha from equation, first equation and second equation. This would be the resulting equation. Notice that we do the same procedure for rectilinear translation. So integrating equation 3 between the limits or condition that the angular displacement varies from 0 to a final value of theta, while the angular velocity changes from an initial value of omega sub o to final value of omega. So we can integrate both sides of the equation 3 and substituting the limit on the left side 0 to theta, on the right side is w sub o to w. So integrating, so this would, we have here equation 4. So equation 5.4 will be for variable forces. Now if the forces or moment, if the moment is constant, so we have equation 5.5. So that is the fundamental work energy equation for rotation. So let's consider applying the work energy equation for system with constant moment. The initial velocity of the block in the figure is 20 feet per second outward at the instant the brake is applied. If the kinetic coefficient of friction at the brake is 0.25, how far does the block descend before stopping? Neglect the dimension of the brake block. So this is the block, 200 pounds. The initial velocity is 20 feet per second. So it's applied on the pulley 2 feet radius. And then there is the outer pulley here, 3 feet radius. The mass moment of inertia is given, 20 foot-pounds per second square. Coefficient of friction in this is 0.25. And from center of the block to the application of force P at 250 pounds is 3 feet. And up to the support hinge at A is 1 foot. For this, we need to draw the free body diagram. So first, free body diagram of the brake lever. So the reacting forces would be the normal force and the frictional force. Then it will be transferred to the pulley. So from the free body diagram of the brake lever, let's take summation of moment at A. We neglect the distance, the thickness of the brake. So we consider only 250 times 4 minus n times 1. So you can solve for the normal reaction. And the force of friction is coefficient of friction times normal reaction. So we got here 250 pounds. Then for the pulley, applying work energy equation to the moving bodies and neglecting the effect of tension. So summation of forces along x is along vertical because motion is along vertical, times distance, plus the net moment times theta is equal to the change in kinetic energy, W over 2G, B sub O square minus B sub O square, that is for the block, plus for this pulley 1/2 I, W square, the final angular velocity, minus the square of the initial angular velocity. There are two systems, the pulley and the block. So that's why we have here change in kinetic energy for the block and the change in kinetic energy for this rotating bodies. Okay, so let us substitute the given. The net force acting on this is the weight. It causes the rotation. 200 times S, the distance traveled, minus, okay, the moment caused by the frictional force about the center, 250 times 3, times theta. We don't know yet what is theta. Is equals to the change in kinetic energy. So W over 2G, final velocity is 0. It will stop. So final velocity is 0. Minus the square of the initial velocity. Plus 1/2 I, that is given 20 in the previous slide, equals to final angular velocity, of course, should be 0 because it will stop, minus the square of the initial angular velocity. What is the distance traveled by this block? That is equals to 2, this radius, times theta, whatever the value of theta. And the linear velocity is equals to angular velocity times the radius. So from this, the distance from center is 2 feet. So that is 2W. Relationship between linear and angular velocity. Or from this, we can solve for theta, that is S over 2, and W is 20 over the initial velocity over the radius. That is 10 radians per second. Substituting the values to the work energy equation, then we can solve for the distance. You can check the calculation if that is correct. The distance traveled before stopping is 12.813 feet. So when you look at the problem or the system, it looks like it's difficult, especially that is rotation. But when you construct the free body diagram of each of the member of the system, and applying the work energy equation, you can easily solve whatever is required in the problem. The important thing is you know how to draw the free body diagram. Now, let's solve problem with variable moment. So this problem, a uniform rod 6 feet long weighing 96.6 pounds, carries a 32.2 pound weight at one end. So it is hinged at A, and at the other end there is the weight 32.2. The weight of the rod is of course concentrated at the center, 3 feet on both sides. As shown in the figure, it starts from rest in a horizontal position, so at this point, and rotates through a vertical arc of 60 degrees, so this one. At this instant, determine the bearing reaction at A. So there will be two, the normal and the tangential reaction at A. So let's consider first moment of inertia of the assembly about A. So this time, you need the formula for mass moment of inertia. For this rod, that is 1/3 ml squared. Whatever the mass times the square of the length times 1/3. Plus, for this weight, W over G K squared. The mass times K squared. K is the distance of this weight to the axis of rotation, and that is equal to the length of the rod. So substituting all the given values, I is 72 foot-pounds second square. The instantaneous acceleration is summation of moment at A, I of A times alpha. So let's get the moment at A, about A. This weight times the vertical component of this distance. So 3 cosine 60 degrees. Plus this weight, 32.2 times the horizontal component of this distance. So that is 6 cosine theta is equal to I alpha. I is 72. So from this equation, we can solve for alpha, angular acceleration 3.3542 radians per second square. Now, let us determine the forces acting on this rod in rotation, including the weight. So, you know this is the centrifugal force, W over G R times alpha. The normal force, the tangential force, W over G R omega squared. So, the same with the weight. Okay? So, W is 96.6, you know, G 32.2 R. From this center up to here, that is 3 feet. Times alpha, we solved already alpha, you get 30.19 pounds. For the tangential, so you know R, 3 feet. Omega, we can solve also omega by the relation of linear and angular velocity. So substituting, we have here 104.57. And for the weight, so substitute the weight 32.2 over G times R alpha. You have one value of acceleration for the system. And this is considering the force tangent to this direction. So 69.715 pounds. Applying work energy equation, the resultant work is equal to the change in kinetic energy. This is the equation for kinetic energy. So the resultant work, 96.6 times 3 sine 60 degrees. Vertical force, so you need the vertical distance. This vertical distance is 3 sine 60 degrees. Plus 32.2. The vertical distance is 6 sine 60 degrees. Equals to 1/2 72 square times W square. Initial velocity is 0. So from that, you can solve for angular velocity, W square. So you substitute here. Applying equilibrium equation for this free body diagram. Summation of forces normal in this direction. Oh, in this direction. This is Rn, this is R tangential. R sub T. So Rn minus 104.57 minus 69.75 minus 96.6 plus 32.2. You solve for the components normal to this. That is multiplied by cosine 30 degrees. This would be 30 degrees equals to 0. Then you can solve for Rn. For R sub t, so you add all these forces. R sub t plus 30.19 plus 104.57, or sorry, this is 20.125 minus the component of the weight tangent perpendicular to this rod. So 96.6 times sine 30 degrees. So the same with 32.2. We just combine here. So you can determine the reaction. 14.085 pounds. So let's apply work energy equation to plane motion. So the translational component of plane motion is equal to the net force times distance, or the resultant work, is equals to W over G times B squared minus B sub O square. The rotational component is summation of moment times d theta is equal to the change in kinetic energy for rotation. So remember, plane motion is a combination of translational and rotational motion. Equating the sum of the left-hand terms of the above equation to the sum of the right-hand equation, we add the left and we add also the right. So the resultant work is equal to the sum of this. So kinetic energy at any instant is given by this equation. Okay, but you can convert this to equivalent angular velocity. So that is RW. So you will substitute R squared W squared. And this would be the kinetic energy. Okay, you can sum up. I sub C is I plus W over G R squared. That is common. So you can substitute in this form. Mass moment of inertia about the instant center. So the change in kinetic energy is given by equation 5.7. So you have to consider the initial angular velocity and the final angular velocity. Considering the plane motion as equivalent to rotation about the instant center, so the moment of the net force about the center times theta, angular displacement, is equal to this equation. We use I sub C. What is I sub C? I plus W over 2G R squared. So equation 5.8. Summation of M sub C is the moment about C of the constant external forces acting during an angular displacement theta. This moment summation about C automatically eliminates the static frictional force holding the instant center momentarily at rest, and indicates that such friction forces do no work on free rolling wheels. If the wheel slips, the equation 5.8 will not be valid. So we shall have to use equation 5.6 on the previous slide and consider the work done by kinetic friction forces. So let's have some problem. Sliders A and B connected by a uniform bar 6 feet long move in the frictionless guide shown in the figure. So where's the figure? So this is the figure. If the system starts with negligible velocity when A is vertically below B, so meaning A is vertically below B, so the rod is vertical. Determine the velocity of A in the given position. So the total height is 4.8. The horizontal distance is 3.6. The length of the rod is 6 feet. When it is in vertical position, the total vertical distance is 6 feet. So the weight of the slider at B is 96.6, the slider at A is 128.8 pounds, and the weight of the rod is 64.4 pounds. So this would be the instant center C. Using the instant center C, the kinematic relation between the bodies are linear velocity is r times angular velocity. B sub B is 3.6, that is the distance from center. 3.6 times angular velocity. For A, this vertical distance, 4.8 times the omega. Whichever do you prepare. The resultant work done on the system are caused by the weights of A and B. The change in kinetic energy in the system is summation of W over G, V squared minus V sub O squared is equals to the change in kinetic energy. This is tangential, this is rotational. Since the initial velocity is negligible, so as I C sub O. Using transfer formula for mass moment of inertia. Okay, I is I plus md squared. So I sub C is 1 over 12 for this times the weight over G. 64.4 over G times 6, that is the length square. That is about the center. Plus 64.4 over G times 3 from here up to here. So that's 3 square. So I sub C is 24.4 foot-pounds second square. This point is at the same level with the instant center. Applying work energy equation, the resultant work is equal to the change in kinetic energy. So what is the resultant work? This 96.6 times the total vertical distance traveled by this. Initially, it's vertical, so the vertical distance is 6. Then it moved. The remaining distance is 4.8. So how much distance is traveled? 6 minus 4.8. And this one, 64.4, the center, is 3 minus 3. So since it's at the center, minus 2.4. So that is 0.6. Equals to change in kinetic energy. W over 2G times B sub A squared, 3.6 square. Plus I sub C, W over 2G. So you have here I sub velocity, 4.8 W square. So for A and B. Plus 1/2, 24, that is I sub C, W square. So from this equation, the only variable is the angular velocity. We can solve for angular velocity. And B sub A is 4.8 times omega. So you can solve for velocity of A, that is 6.78 feet per second. So that is the application of work energy equation to plane motion. Okay, so that's the end of the presentation. So thank you for listening.